This is the first video for the Seqr module, Series and Sequences. In this video we're looking at sections A and the first part of section B. To begin, let's look at our objectives of the Seqr module. Firstly, to distinguish between arithmetic and geometric sequences and series. We are only going to really be looking at arithmetic and geometric series and sequences. To understand and use sigma notation. Now sigma is the sum of symbol. To determine terms, common differences or common ratios of arithmetic and geometric sequences, to determine the sum of terms for arithmetic and geometric series, to find the sum of an infinite geometric series, to solve problems involving arithmetic and geometric sequences and series, to use mathematical induction to prove relationships, to determine and use a recursion formula, and use Pascal's triangle and the binomial theorem to perform binomial expansions. To begin, let's just look at what a sequence is. Okay, a sequence is a set of numbers or symbols which display a certain pattern. So a common one might be 2, 4, 6, 8, etc. Okay, these are our even numbers, so we're timesing by 2 each time. Okay, this is called geometric because we are multiplying. Okay, we could also have something like this. Okay, for this one, to get it to the next term, I'm actually adding 3. This is what we call an arithmetic sequence. We could also use symbols. So if I was looking at matchsticks, making triangles, you can see here that I'm adding 2 matchsticks every time. So with that, going back, each member of a sequence is called a term. So we have this 2 is a term, the 4 is a term, 6 is a term, 2 is considered to be the first term, 8 is the fourth term, etc. Okay, now for each sequence below, describe how the terms are generated and then determine the next 3 terms of the sequence. So if we look at the first one here, we can see where we have a pattern. Okay, now what is the pattern? Well, we start with a triangle. Okay, so we think about what's happening here. Our first term is a triangle, and that has 3 sides. Our second term is a square, which has 4 sides. Then we have a pentagon, which is 5 sides. So to describe the pattern here, you'd be saying the figures are regular polygons, regular meaning equal sides, and each successive figure has 1 more side than the previous polygon. So you would need to write that down. That's written in your textbook for you to refer to. Second part, determine the next 3 terms in the sequence. Well, we'd have to have 6 sides, which would be a hexagon. I'm not too sure how I'm going to go with drawing these. All sides would have to be equal, but get the idea. Then 7 sides, which is a heptagon. And I'm not going to try and draw that. You can see one in your textbook. And then at 8 sides, which is an octagon. Again, you'll see one drawn in your textbook. And it helps if I spell that correctly. Okay, the next one, 4, 6, 8, 10, 12. So when you're looking at this, each term is increasing by 2. So we're adding 2 each time. So part A is each term is 2 more than the previous term. Okay, and then part B, the next 3 terms, well, you'd have 12 plus 2 is 14, 14 plus 2 is 16, 16 plus 2 is 18. Next one. Half, 2/3, 3/4, 4/5. Well, you should be able to see that the numerator, which is the top, is increasing by 1, whilst the denominator is also increasing by 1. Now if I let n be 1, then that means each time my formula is going to be n over n plus 1. So 1 over 2. If n was 2, I'd have 2 over 3. If n was 3, 3 over 4. Okay, and our next three terms would be 5 over 6, 6 over 7, 7 over 8. Okay, what now? There's an exercise in your textbook, Seqr Ab 1. Complete that and make sure you check that you're correct.